Welcome to Algebra 2. Today we've got section 9.2, angles and radian measure. Now I had mentioned when we were going through section 9.1 to make sure that your calculator was in degree mode. And in the second part of 9.1, when we were using our inverse trig functions and finding angles, I said that if you do not put a degree symbol on that answer, that it is horribly wrong. And there's a reason for that. If you are talking about an angle and you just have a number describing the measure of the angle, it is implied that you are giving a radian measure of an angle. Now, this is something that you probably have not seen yet, so it's some new vocabulary, but it actually makes working with some of our future angles that we will see, makes it much easier, much more connective to what we are going to do in the future. So we want to establish this idea of what a radian is and how it's useful right away. And that's the purpose of today's lesson. So let's have a look, I guess. All right, one of our first tasks is going to be drawing an angle in standard position. And it could be in degrees, it could be in radians, but the angle will have an initial side in the positive x-axis, and then the terminal side will rotate like clock hands around the origin to create the angle. So here I got a little illustration. We've got our initial side in blue, and then we rotate the terminal side into position, and that creates our angle. So how that terminal side rotated, that's what our angle is measuring. Okay, really nice visual. Now, we had gotten an answer in yesterday's lesson where we got a negative angle, or we got an angle that was obtuse. Well, you can now see how that's happening, because we can have positive and negative angles because we're giving them a direction to rotate from that initial side, that initial positive x-axis location. So positive angles are measured counterclockwise. Negative angles are measured clockwise. Okay, and the connective tissue, I don't know if anybody's ever heard of quadrants before. I'm sure you have when you first learned of graphing on the XY plane. They're labeled in Roman numerals. And you've ever wondered, hey, why do those go counterclockwise? Doesn't it make sense that they would just like go clockwise and starting in the top left, you know, like we read? Well, no, because when we're rotating a positive angle through, that's the order that it follows. So it's to make our XY coordinate plane match perfectly with angles as well that we've done this. So that's why they're numbered that way. All right. So the difference between degrees and radians. An angle measured in degrees is measured as if you'd had a protractor like zeroed out on the origin. Right, so we have our initial side right here. Line that up with 0 on our protractor, and then we've got so many tick marks that we count out until we get to our terminal side, and we would have like a theta equals, I don't know, this would be like 58 degrees or something like that. Each degree is a little unit along that protractor. Well, an angle measured in radians is measured as if it were like a little arc that's a fraction of the circumference of a circle with radius 1. Okay, so a radian measure then, if we have our initial side right here, well then, if I were to go all the way around a full circle, well, the circumference equals 2 pi r. So if I'm on a radius 1, circumference is 2 pi. So if I'm going to move my terminal side, let's say right here, well, then that would be 1, 2, 3, 4. That would be like 1/6 of the way to pi radians, you know, halfway around the circle. So if I had 1/6 of pi, I'd get a fraction like that, pi over 6. And that is what these radian measures look like. They can be decimals or whole numbers as well, but it's denoted as being a fraction of 2 pi. It's a little arc length. Okay, now why is this so helpful? Well, if it incorporates the 2 pi, it incorporates the circumference of a circle, we get some really nice geometry to come out of this. So I don't know if you're in any of my geometry classes, when we were doing arc length, what we would do is we would say, okay, it's the angle over 360 times 2 pi r. Well, since our angle is going to be in radians here, that takes care of the fraction of the circle part. So it's just 2 pi, 2 pi r, and that fraction of 2 pi has already been accounted for. It makes the formula much simpler to work with. And the same goes for area. If it's if it's pi r squared for area, and then some fraction of that, again, if you're in my geometry class, this is what we're doing. Our central angle over 360 times pi r squared. Well, now you can see we don't have a fraction of a 2 pi circle, so that's why they need the 1/2 in there to balance it out. But we still have our radius squared, and then the theta is taking care of all that fraction work. You get much simpler geometry formulas when we're working in radians, and that's why we have them. All right, well, what we have is really a simple proportion, right? So where these formulas are coming from, these conversions are coming from, they should just make sense, because if I think about it, if I have 35 degrees out of a full circle would be 360 degrees, and that equals some number of radians out of 2 pi radians. Well, what's going to happen? To solve for x, I would need to multiply by 2 pi. So I've got my 35 degrees times 2 pi over 360. And then when they've simplified that to, instead of 2 pi over 360, made it 1 pi over 180. So all they're doing is cross-multiplying, really, solving that proportion and simplifying it for you. And the last thing is, we can have angles that are over 180 degrees now, and we haven't seen that yet. So if we imagine, let's say we drew like a 225 degree angle. So we'd start on our positive x-axis, we would rotate, here's 180 degrees, and then 45 degrees past that would be our terminal side. So that's 225 degrees. Well, since we can rotate indefinitely, if I started on that initial side and I rotated a full circle and then came around to that, I would end up with the same terminal side. It would essentially be the same product at the end. The clock hands just spun through an additional rotation. Right? Just like 7:30 in the morning is the same clock hand position as 7:30 in the evening, we have coterminal angles that do that. We have the same ending position of the initial and terminal side. So how do we arrive at that? Well, we just add or subtract some multiple of 360 if we're in degrees, or 2 pi if we're in radians, just to find different angles that will lead us to that same ending point. And this is often useful if someone were to ask us, hey, what's the sine of 900 degrees? We'd want to find a coterminal angle that was smaller than 900 so that we could easily draw it and work with it. So that's why we have them, to handle large angle measures. Okay, our first example is just to draw the angle in standard position, just get a feel for what quadrant we're going to end up in, and how am I rotating that terminal side around. So actually, I would pause the video if I were you and try this on your own. I'll check back in a couple seconds with the solution. And okay, I think we should have, hopefully you took the time to pause the video and give this a shot on your own. Let's compare and see what we've got. So just in my mind, you don't have to label this every time, but here's 0 degrees, 90 degrees, 180 degrees, and then if I go another 90, I'd have 270 degrees down here. So those are good benchmarks to use, those axes. So my initial side is here. I'm rotating through 180 degrees, and then I go 35 degrees further. Should end up with a terminal side that looks like that. Okay, of course, we want to label that little arc that shows the rotation through so we know exactly how many degrees we've moved. For number 6, 450, well, 90, 180, 270, 360, and then another 90 degrees. I end up with a perfect right angle there that's 450 degrees. And sure enough, if I subtracted 360, I would end up with a 90-degree angle as a coterminal angle. So it makes sense. Number 8, negative 10 degrees. Here's my initial side. Since it's a negative angle, I'm rotating clockwise, and I don't go very far. This is actually a gross exaggeration just so I could fit the label inside. But a 10-degree angle should not be going that low, that far beneath the positive x-axis. Negative 105 degrees for letter B over here. Well, initial side going in the negative direction, there's 90, and I'm going just 20 degrees past that. There's negative 105 degrees. I'm sorry, 15, not 20 degrees past. I thought I was doing 110 for whatever reason. Okay, and I just noticed I did not label this as negative 10 degrees. Next one, letter C. Initial side, 80 degrees. I'm almost getting to 90 degrees. There's my angle. And the last one, letter D, 380 degrees in the negative direction. I go a full circle in the negative direction and then 20 degrees further. There we have it. So we have all of our angles just practiced. What quadrants should we end up in? Getting used to those benchmarks and how does that terminal side move through as it rotates either clockwise or counterclockwise. All right, number 2, or example 2, find a positive and negative coterminal angle for each given angle. All right, well, if I'm at 255, that's already positive, so 255 plus another 360 will give me a positive coterminal angle. It's going to be huge. It's going to be huge, but it will be a positive coterminal angle. I can't subtract 360 because then I'd be negative. I get 615 degrees. There's my positive. And if I took that starting angle of 255 and subtract away a full circle, then I get negative 105 degrees. So an angle that's negative but coterminal with 255. Hey, you can always make a quick sketch to help visualize this as well. And we can keep adding or subtracting to our starting angle to keep finding additional ones as well. So like for number 12, if I have negative 800 degrees, well, if I add 360, a full circle to that, I'm still going to be negative. I'm going to have negative 540 degrees. So there's one coterminal angle. Well, I'm sorry, it'd be negative 440 degrees. Okay, so then if I take that negative 440 and add 360 to it, I'll have negative 80 degrees. I'm not going to box that one up because it's not a positive coterminal angle yet. So I'm going to take that, I'm going to add another 360 to it. That gives me positive 280 degrees. Now I've gotten to the positives. For that coterminal angle just by repeatedly adding 360. All right, our next task, convert between degrees and radians. My little mental trick here is know what you're starting with, And then depending on what you're starting with, what are you trying to cancel out? So in the case of number 14, I'm starting off with degrees. That means I want to cancel out degrees. So that means I want to divide by 180 degrees. That's what kind of helps me remember, is it pi over 180 or 180 over pi? What am I trying to cancel out? So if I do this, my degrees as units, kind of like dimensional analysis in chemistry, I would get the fraction 315 pi over 180, and then I can simplify. 315 and 180 are both divisible by 45. Yeah, so I get 7 pi over 4. We just simplify the fraction. For number 18, here I'm starting with radians. I want to cancel out the pi. So I'm going to multiply by 180 degrees over pi, and that will cancel out. I've got 3 times 180 divided by 4. Okay. 3 times 180 divided by 4, that simplifies to 135 degrees. And we can use a calculator to help with that, obviously. For our number 14, we obviously just would have done 315 over 180, and then use the calculator to simplify the fraction. Just know that there's a pi left in the numerator. And then number 20, here's the case where we have a radian measure, even though it looks like it should be a degree, like somebody just had a typo and left the degree symbol off. But this is technically a radian measure, so just like number 18, I want to multiply that by 180 and divide it by pi, and I'm just going to end up with some decimal. Use the calculator for this. So 12 times 180 divided by, and I'm going to use the pi key, I get 607.55. And remember, I converted this into degrees, so I need that degree symbol. So now you can see why if you say we solved a problem and our answer was supposed to be 12 degrees, if you left the degree symbol off, that's how far off you were. Instead of 12 degrees, like you meant your answer to be, you actually wrote 12 radians, which is 607 degrees. So you were off by a whole heck of a lot. Okay, and our final example here, now using some of those new geometry formulas, if I have radian measure for my angles, this is so easy. In the men's shot put event at the 2012 Summer Olympic Games, the length of the winning shot was 21.89 meters. A shot must land within a sector having a central angle of 34.92 degrees to be considered fair. The officials draw the arc across the fair landing area. You can see they got those out of bounds lines drawn on the left and right. We want to find the length of the arc that has the longest throw. Okay. So what that's telling us is from this spot in the ring, competitor throws 21.89 meters. If we were to measure that arc, what would the length of that arc be? And again, let's use our radian angles. Holy cow, do they make the geometry easier. So 34.92 degrees, I want to cancel out the degrees. So let's see what that would be in radians. And I'm just going to come up with a decimal radian answer and round it to like 3 or 4 decimal places so I'm sure it's accurate. 34.92 times pi divided by 180 equals, that's 0.6095. And again, that's my radian angle. Sometimes those are labeled RADS for radians. But now if I have that, the length, S, it just equals R times theta. So in this case, S would equal 21.89 times 0.6095. 21.89 times 0.6095, 13.34 meters. Okay. Letter B says all fair throws landed within a sector bounded by the arc in part A. What is the area of this sector? Okay, well again, that radian angle is going to be crucial because our area is 1/2 r squared theta. So in this case, that's 1/2 times 21.89, that's our radius, squared, times that 0.6095. And that's going to calculate all the area in here. Let's find out how many square meters that is. 0.5 times 21.89 squared times 0.6095. And I get 146.03. And I tell you what, when you think about going back to geometry class and all that angle over 360 times 2 pi r squared stuff, man, do these radian angles make the geometry work a lot easier. That does it for section 9.2 here in Algebra 2. Here's a look at your assignment.